In this video, I'm going to show you how we can compute the values of E, D, and the twoshent. I'm going to demonstrate the computing of these variables for the RSA encryption systems. We'll use Spider. So this is a simple math. I will not use predefined or the third-party libraries or modules to generate those keys. I'm going to show you by directly write the functions and the equations in order to solve or to get those private key and public key for the RSA crypto system. So in the first thing, you need to define or select two prime numbers. These prime numbers are namely P and Q. So you will choose here. I'm going to start over here. I'm sharing in the line 52. Here I have generated a prime number from 1 up to 100. So this is the primes that have the list of primes from 1 up to 100. In practice, for a real project that uses RSA, the prime numbers between such a kind of numbers will be used, such kind of these numbers, from 1,000 million to some kind of huge numbers. Okay, but that is also a computational hard. It is hard to generate those numbers. So I'm going to use, for a simplicity, prime numbers between 1 and 100. And then I will select P and Q randomly from these prime numbers. These prime numbers are P and Q must be generated separately. Nobody has to know these two numbers. So I've used the print statement to print the values of P and Q here. Then I'm going to print N. This is publicly available. This N, the product of these two primes, N, will be used as or published for the public domain. So everybody can see this N. Since we will use this N to encrypt and decrypt messages. So here I print N here. And here is the Euler twoshent. I'm going to, again, this is secret. The twoshent must be also secret. Nobody has to know it. And the ETN is the twoshent of N, which is we know N is P times Q. So then the twoshent is P minus 1 times Q minus 1. So this is a twoshent. I'm going to declare a variable and call it ETN. So here I'm going to see ETN as here. For instance, you can see this console. P were 49, Q were 3, and N is that the product of this is 1 to 3, and ETN were 80. Now I'm going to get E. E is a public key. So for the public key, we will use two numbers, E and N. So this will be known by everybody else. E, the variable E in the variable N will be published for the public to use the encryption and decryption. But the variable D and the ETN must be hidden from everybody else. So what is E? E is relatively prime to the twoshent. So relatively prime means I'm going to use randomly one relatively prime to the twoshent. What does it mean? I'm going to generate the co-prime numbers up to ETN. Now, what is coprime numbers? Coprime numbers given ATN or any value of n. Here I'm going to see this one. Look at this one. I don't have to use semicolon around here. Here, from 2 up to n, there must be, if any number from 2 up to n, if any number that cannot divide n, except one and the value itself. If that number cannot divide, that number, it is considered as a prime or relatively prime, or the greatest common division of any number I between in the range 2 up to n, the GCD must be 1. So that is a coprime number of any given number. So I'm going to generate a coprime numbers up to 4 ETNs. Then from that, I'm going to choose E randomly. Now, E is a relatively prime to the ETN. Now, good. Now, the private key is D. I'll use printf statement to see the value of E. Now, D is also must be a relatively prime number to ETN also. D and E are relatively prime numbers from relatively prime numbers of ETN. So if E is relatively prime numbers to the quotient, and D must be the must be the relatively prime number to D in order to work the RSA as we need. So D, we are going to compute D, but again the product of D times E modular to the quotient must be equal to 1. So D has to be satisfied. First, D must be the coprime numbers to the quotient, as well as D times E mod the quotient must be 1. So we are going to look at or find D that satisfies these two requirements. The first thing is D must be the coprime number of the quotient, and D has to satisfy D inverse must be E D times E is equal to, let me open up some kind of notes. So here, this must be E times D mod the quotient. This is a quotient ETN, this phi of 9 must be equal to 1. That means E inverse must be equal to D times mod this quotient. Or in other words, E times mod the quotient is D, but again D, the inverse D must be a coprime number, up to the quotient. Then to compute that one, here I have called the function compute D. Here it is the compute D function that will accept E, ETN, and coprimes. Then I will the coprimes are the coprimes number up to ETN. I'm going to look at D that satisfies D times E modular of ETN must be equal to 1. If it does, if D satisfies such equation, then I will return that D. So this is D and this is E. So after we generate this, the required variables ETN, N and ED, the pair of N, this one N and E, published as a public key, and D and N must be kept private. This obviously N is also publicly published. So let me give you an example. If M is 4, if this means that M must be less than N, so if let M is a message that we are going to send over the network. So M is 4, and the ciphertext of M or any kind of message is M the power of E mod n. So we will send this C on the cable, on the wire, and on the receiver side, the receiver knows D as well as E, because this is a public and this is the private key. Then we will power C to the power D mod n, so we can extract the value or the message from the ciphertext as like this. So you can print a message M. For this simple P, we select P and Q are 41 and 3, and the product of these are 123, and we select ETN, which is 40 times 2 is 80, and E is relatively prime to ETN, so that satisfies 29. We select this randomly. Then we will select also prime, relatively prime to this 80, but that satisfies D times E mod 80 must be 1. So we select D because this 69 satisfies such a requirement. Then after that, given a message 4, we will do 4 the power of E mod n, then that will become 31. So to get the original value from this C, we must use D. So D is private. So if anybody does not know D, then it will be hard for him to find the message. But the owner has already that key. So if you multiply C 69 times, and if you perform mod n, you will find the exact value. For instance, let me use 14 or whatever 17. Let me execute it again. So P were 47 and P is 41, randomly selected. N is here, and ETN is here, E is here, D is here, M were 17, C is this one. Then we get back the value 17 again. Hope this video is useful for you, and in the next video we are going to use another technique called the Euclidean algorithm to find the D, to compute D, and with that we will see quantum algorithm to factor n. So this is a prime factorization problem given n. This is publicly available, as I told you earlier. So we have to find P and Q that will give us this number. So we will use the prime factorization or the Shor's algorithm to find a given number. And after that, I will show you my proposed article that factors this number using Grover's algorithm. Hope this video is useful for you. Don't forget to subscribe. See you in the next video.